Just a couple reminders before we get into today's lecture. So the first thing is Lab 3 is due today. Second thing is that we have another quiz coming up soon. It's going to be next Friday, and it'll cover lectures 6 through 12. And we're going to have, once again, a quiz review next Tuesday evening from 7:30 to 9. You'll get more information about it, but that's going to be held in room 10250. All right, so today we're going to be learning about, first of all, we're going to finish a couple of things that we didn't get to do in last lecture, and then we're going to talk about what does the template look like for procedures, which is going to be the main topic of today. All right, so, sorry, very quickly, I wanted to, so this slide we saw last time. This is basically just the templates of how you take expressions in C and convert them into beta assembly. I'm only including this here so that you can use it for reference. And this is where we stopped last time. So I'm assuming that at this point you've seen some of this recitation, so let's try to go through it a little more quickly. So basically what we had here is we have an assignment where we want to assign y equal to this complicated expression. And so we are going to call compile expression on this long complicated thing. And we also saw that when we have an assignment, then what that means is you're going to have, eventually you're going to store something into y, but first you're going to go and evaluate what the inner expression is. And so we call compile expression on this inner thing. And we keep doing that recursively until we get to a point where we can actually produce an assembly instruction. So we split this up into two and call compile expression on x minus 3. That brings us down to compile expression on x. And now the corresponding assembly that goes with this is to load the value x into a register. Okay? And so we have some x defined here in memory, and we can now load that value into R1. Okay, we then continue with the next expression, which is 3. And so the translation of that into assembly is C move 3 into another register. And now we're ready to do our subtract. And so now we can subtract R2 from R1 and store that result into R1. And we're going to need to maintain that for later multiplying with this other expression. Okay, so now we can move on to the other expression. And we do the same kind of thing where we're going to get to compile y. That's basically a load of y into another register that's not currently used. We have this long constant, and so because this needs more than 16 bits to represent, that means that we're going to actually have to store that constant in memory somewhere. So we store it in a location we happen to call C1. And so now that we have that location, we can load the contents of location C1 into yet another register. Now we can add R2 and R3 together to produce this y plus 1, 2, 3, 4, 5, 6. And now we're ready to do the multiply of the result from the subtract and this add. And so now we have our result of the entire expression here in R1. So the last thing that we want to do is store that final result into y. And if you basically take all of these instructions, you'll see that this is the list of instructions that we end up with in order to, after we've compiled this expression into our beta assembly. Now, highlighted here in yellow, we have a minor optimization which we can make. So if you look at adjacent instructions, you notice here that we have a C move that's followed by a subtract instruction. And actually, because we have in our beta operations that allow you to do a register with a constant ALU operation as one operation, we can actually merge these two into a sub-C instruction and thus get rid of one of our instructions. Okay, and so we call these peephole optimizations because they're only considering instructions that are right next to each other. Later we'll talk a little bit more about other types of optimizations that one could make. Okay, so we've completed the compile expression. We now move on to compile statement. And so we had 4 kinds of statements that we mentioned in last lecture. We're going to see what we do with each of them. So the first is you just have an unconditional type of statement, and so it's made up of an expression. So all you have to do here is call compile expression on this expression, and then you run the previous details for the compile expression routine. The second type of statement we have is a compound statement, and this is basically just a sequence of statements that it should be executed one after the other. And so again, this is a very simple translation where we're just going to call compile statement on statement 1. We're going to produce whatever assembly that produces, and then we're going to call compile statement on statement 2, and the instructions produced by that will simply immediately follow the ones produced for statement 1. Here we have a conditional. Okay, so how do we handle conditionals? Again, not very complicated. What we want to do here is if this expression is true, then execute the statement. So the first thing we have to do is compile this expression and store that value into Rx. Now that we have it in Rx, we can do some decisions, make some decisions based on it. And so what we've got here is a branch on false Rx. In other words, if the expression is not true, then you don't want to execute the statement. So you jump over to this end if label. However, if it is true, then you do want to compile a statement, and so then you call compile statement on this. And again, this might recursively call other compile expressions or other compile statements, but eventually you'll get to a point where you know how to translate it into a beta instruction. This is just a slightly more complicated form where we also have an else statement. And so here again, we start the same way. We compile our expression, which is telling us whether to do the if or the else. And then if it's false, that means we want to jump to the else and then compile statement 2. If it's not false, then we compile statement 1. And then we skip compiling statement 2 by branching to end if after that. Okay? Just a couple more of these. So we've got also iteration, which is a while loop, which is basically saying, while this expression is true, I want to keep executing this statement. And so what that gets translated into is we have this label L while, and we call compile expression on this expression, store that value into Rx. And now we can make some branches depending on what we found that expression to be. So if it's false, that means we don't want to execute the statement, so we jump to the end of this. If it's true, we just come in here and do the compile statement, and then we branch back to L while. Now, you can optimize this just a bit by getting rid of one of these branches inside your main loop. And the way that you would do that is you simply move your test condition to the end. And so you first have to branch to your test. Here's your test code. You now do compile expression, put that result into Rx, and then if it's true, then you're going to go and execute your while, which will allow you to do this statement. If it's not, then you're just done. Okay? And then the last one here is a for loop, which is very similar to a while in that you're doing iteration. And so essentially what this translates into is it says you're going to initialize your variable to whatever it says over here, then you're going to repeat the loop as long as this expression is true, and this is going to be how you increment your variable in order to eventually end this loop. And so you can very easily translate this into, first you do your initialization, and then you convert it to a while this test statement, which is this I less than 10, or the thing that goes here in the middle, then execute the statement and follow that by your increment, okay? And so in this way, we now know how to assemble for loops as well, okay? So we basically have these templates. We now know how to create our assembly code for loops, while loops, if statements, and any kind of basic expressions. So putting this all together, if you were to follow all of these templates for this piece of C code over here on the left, then you would arrive at this assembly code in beta, all right? And so it's relatively easy. So as far as being able to translate it and produce it, not a hard thing to do. what's not so good about it yet is that right now we have 10 instructions in our loop, right? Our loop starts here and it ends all the way over here. So it would be nice if we could do some simple optimizations to make that better. And it turns out that we can. There's a very simple optimization that can be done, which is that instead of constantly loading and storing things back and forth from memory, that we keep things in registers, especially within a loop. So what happens here is you would do your loads into some register before you begin your loop. Then within the loop, all the operations are on the registers themselves. And so you notice that now I've gone down from 10 instructions to 4. And then at the very end, I store my results back into their locations in memory. There's no need for me to store all of those intermediate results. I only need to store the final one in memory. Okay? Any questions about that before we move on to procedures? All right, good. So today we're going to be learning about procedures and stacks. And so ultimately, by the end of today's lecture, we'll also have a template for how you would go about compiling a C procedure into a beta assembly. It's going to be a little more complicated than, than these other statements that we saw, but hopefully it'll all be clear about how we want to do that by the end of today. So what is a procedure? Well, a procedure is basically a reusable piece of code. And so I can create an abstraction of a function. Let's say here I have a greatest common divisor function. And I can write code that just implements this function. And then from my main code, I can call this function. And so I could call it once, I could call it many times, I could call it with different arguments. And each time I would just reuse this piece of code. Okay, so what does that level of abstraction buy me? Well, it buys me a couple things. First of all, it's much, much easier for me to write the code, because at any point in time, instead of having to constantly put in that entire GCD procedure, I can just make a call to a procedure. So so let's see what the elements of an actual procedure are. So the first thing is that it's got a single named entry point. So where we have this name, this is basically going to correspond to where does the beginning of our function, where does the description of our function begin. We then have 0 or more variables and a specification of what kind of variables they are. So here we have variables a and b, and they're both integers. In the procedure, you can also have local variables. So these variables x and y are just local to our procedure, and they basically disappear once I'm done executing the procedure. But it might be the case that you want to do some kind of intermediate calculations for which you might want to have some extra variables to work with, and so you can define those locally to the procedure itself. And essentially what that translates into is that you would be, when you're executing the procedure, you would be allocating some location in memory for these variables, and when you return from this procedure, you deallocate them, and then that memory is no longer used. Okay, and finally, procedures will generally have a return statement. It is okay to not return any value, in which case the reason that you called the procedure is for whatever side effect it happened to have caused. But often you will also see that it is actually returning a value, and the type of this value is specified up here right before the name. Okay, so this GCD procedure is returning an integer. And by calling this return, it's going back to continue executing from the place that made the call to this procedure. Okay, so we're seeing, very quickly that this is a pretty powerful abstraction, right? We can write lots of code with lots of different procedures, and each procedure doesn't really need to know about the implementation of another one. So for example, here, if we look at this coprimes procedure, you see that it simply calls GCD. And so all it needs to know is that a function GCD exists, It needs to know the basic operation of, what are the inputs it takes and what does it produce, but it doesn't need to know anything about the actual implementation of that procedure. All right, so let's start thinking about how we can go about implementing these procedures on our beta and in general on any kind of processor. So one option that we can consider is that anytime that there's a call to a procedure, that we would basically replace that procedure call with the code that corresponds to that procedure. This is known as inlining. So there are some problems with this. So can anyone think of an obvious problem with using inlining? Yeah. What's that? It'll get really big, exactly. So code size is a huge problem, right? If I have, 100 calls to this GCD procedure, and every time I'm calling it, I have to replicate that entire piece of code, my code is going to get very big very quickly. It gets even worse when we deal with recursion, right? So what happens in recursion? Here we've got the definition for factorial, and in factorial, what happens is that you within the procedure call factorial again, and then you call, once you're executing that factorial, you're going to call it again until you reach this ending condition, which is when n is not greater than 0 anymore. And so if you were to try to translate this by inlining, you would essentially end up with a situation where your translation never ends, right? Because you would inline this first factorial, but then within that you'd have to inline this factorial, and within that you'd have to inline the next one, and so on and so forth. Okay, so we have to come up with something that works better than that. I will say that there are some instances where inlining makes sense. Some examples of this include, if you have a very short procedure, and you don't necessarily use it many, many times, then it might actually turn out that the compiler chooses to inline that code, because otherwise, as you'll see as we go through today's lecture, handling it in a more generic way has some overhead costs. So sometimes for very small procedures, you might not want to pay that overhead. But more often than not, you will want to do it the more generic way. Okay, so what is this more generic way? The generic way is this notion of linking. So what you're going to do is you're going to produce different code for each of your procedures, and you have responsibilities both on the caller side, the person who, the piece of code that's making the call to this procedure, and on the callee side, the code within the procedure itself. And those responsibilities include the following. So on the calling side, you have to pass some input arguments, and if you need to do some evaluation in order to figure out what those arguments are, then you need to do that as well. And you need to also pass control to the procedure itself, so that it can then do what it needs to do. Once you pass that control, then the code associated with the procedure is going to run. It's going to store the result that is the result of that instance of running the procedure, and then it should transfer control back to the caller. Okay, so at a high level, that's what we want to do. So let's take a look at our factorial instruction procedure and try to iron out the details associated with this. So first of all, if suppose we want to call factorial on the value 3, we see that factorial of 3 is going to return 3 times factorial of 2. Factorial of 2 is going to depend on factorial of 1. Factorial of 1 depends on factorial of 0. And finally, factorial of 0 returns a constant. So there are a couple things that we're going to have to do here every time we call factorial again. So the first is we're going to want to pass an argument, right? So let's just say that our convention, for argument's sake, is to pass the argument in R1. Okay, so we'll do that. Then we also want to pass the return address, and we'll use a special register for that. We'll call it R28. And if you recall from a couple lectures ago, we saw that by storing that return address into some register, then the way that we can call procedures is you simply have a branch instruction that goes to the label associated with a procedure. In R28, you're storing your return address, which is the address of the instruction immediately after the branch. And then when you finish your procedure, you just have a jump to R28, which brings you back to the instruction immediately following the call to your procedure. And finally, our last piece of convention is going to be that we can assume that the result from the procedure is going to be put into R0. So when you pass control back to the callee, it knows where to find that result. Okay? All right, so here's our first try at actually making use of these conventions in order to translate our factorial function. Okay, so what do we have here? First thing we have is we're calling factorial of 3. So we said the caller is responsible for putting that argument into R1, right? So we see here a C move 3 into R1. Okay, so we've achieved that part so far, so good. The next thing we're going to do is we're going to transfer the control to the procedure, and we're going to store our return address. So we have a branch to factorial, and we store the return address into R28. Okay? Now we move into the code within the procedure. So here, we're going to be doing this check of whether or not n is greater than 0. In our beta, we don't actually have greater than comparisons. We only have equal or less than. So what's happening here is that it's being flipped. And then if the opposite comparison is true, then you're branching to your else condition. Otherwise, you're going to go ahead and execute the code associated with the if. And what happens here within the if is that we have this recursive call to factorial, which is calling it with the argument n minus 1. So what do we have to do here? Once again, we need to put our argument into R1. So what you see we did here is we saved the value of n because we're going to need it when we come back in order to do this multiplication by n. But then we went ahead and calculated n minus 1, put that into R1, and once again we called branch factorial, comma R28 in order to save the return address. Well, when we return from this, what we expect to happen is that we'll be able to multiply the return, what was returned by this recursive call times n, which was stored in R2, and that will put our final result into R0, and at that point we can return to our main code. Well, so who thinks this actually works? And if you don't, maybe you can tell me why. Yeah. That's exactly right. So this doesn't work because look at what we've done here. We have R28 over here, which is where we stored our return address from the main program. Okay? So this R28 has the address of this halt instruction. Okay? But when we went into our factorial and we called factorial recursively, we stored something else in R28. What we stored is the address of this multiply. And so all of a sudden, when I want to do this jump back to this halt instruction, the value of R28 is gone. Okay? So we're getting a little bit closer to figuring out how to do this, but we're not quite there. All right. So let's think about what every single call of the procedure actually needs in order to work properly. So we've talked about input arguments. We've talked about needing to know the address to return to when it's done executing its instance of the procedure. And we have to have a place to store the result. We also might need to store some local variables. So while I'm computing things, it's not necessarily okay for me to just assume I can use my 32 registers, right? It might be the case that whoever called this procedure is expecting a value to stay put in one of those registers, if not in all, right? So what we want to do is we want to make sure that we have a way to save that information. So how might we do that? What we're going to do is we're going to basically create a portion of memory that's associated with every single instantiation of a procedure call. And what we call that is an activation record. So let's look a little bit in more detail into what will actually make up an activation record. So here we've got our factorial, and we begin by calling factorial of 3, right? And we saw that factorial of 3 is going to make a recursive call to factorial of 2. However, we want to make sure that anything that we need to keep from that first call to factorial of 3 sticks around. So what we're going to do is we're going to create a second activation record. And so we're going to have, you know, 2 portions of memory keeping whatever it is that we need to keep, whether it's, you know, the arguments, registers, anything else. And we'll get into the details of that in a moment. Now, factorial 2 calls factorial 1. Factorial 1 calls factorial 0. And now we're done with our recursion. Okay, so now what we can do is we've gotten to the deepest point where we have 4 activation records that we have to keep track of all at once. And now when we're done with factorial 0, we're not actually going to go back to it. So we take it away. We basically forget about that information in memory. And we continue to do the same thing with factorial 1, then 2, and finally we're back to just 1 activation record. Okay? So let's take a closer look at what's going to go into these activation records and how we might go about implementing it. So the first thing is that we want to introduce this concept of a stack. So early people who used to do compilers early on, what they realized is that when they wanted to compile their programs, it was generally the case, or it was always the case, I should say, that what they wanted to do was put activation records in what's called a last in, first out order, okay? So it's always the case that the last thing that you put in is going to be the first thing that you take out, okay? So that suggests that we need some new kind of data structure that enables dealing with data in that way, okay? And that data structure is a stack, okay? So basically the way that a stack works is it's a portion of memory, and you have 2 main operations that you use in order to deal with the stack. You have a push operation, which puts something onto the stack, and a pop operation, which takes the top element of your stack and takes it off the stack. So, for example, if we have this factorial 3, we would then put factorial 2, factorial 1, and now it's going in reverse and taking it off the stack. Okay, so the idea is you, as we saw with the activation records, you are going to put things on in one order, take them off in the reverse order. And what we'll find is that in C, things are actually fairly simple because at any instance of a particular procedure, you only actually need to be looking at the activation record associated with that instantiation of the procedure. There are actually other programming languages where that's not true, where you might need to access other activation records, and stacks do support that as well. But in our situation, we won't need to worry about that. Okay, so let's think about what our stack implementation is going to look like. All right, so the first thing that we're going to do is we're going to use another one of our registers for a special purpose. It's going to be called our stack pointer, and we're going to use register R29 in our beta for our stack pointer. So this stack pointer points to an unused location in our stack. And the convention is, what happens is our stack starts at lower addresses, and every time we push something onto the stack, we're pushing it onto a higher address, okay? And the stack pointer itself is always pointing to the next unused location. So if, let's say, my stack pointer is currently address 0x104, then it means that everything below that address has already been, had some value put into it on the stack. So the great thing about stacks is that we can really use it whenever we want. So one perfect example of this is if we run out of registers, and we'll go into detail and an example about that in a second. But the key thing is the stack essentially gives you additional storage that you otherwise didn't have available to you. And the one piece of discipline that you have to maintain is that you always have to return the stack exactly in the same state that you received it. And the one last note about our stack implementation is that we're going to pick in our beta a location that's far away from, from our instructions and where we're keeping our data so that there's no interference as we're pushing and popping, as we're pushing particularly things onto the stack. We're not going to somehow overwrite our instructions. Yes?
Is there a limit to the size of memory that you reserve for the stack? And if so, how do you, does that also imply that there's a limit for the number of recursive calls you can have?
Ultimately, yes. I mean, your memory, it does have a size limit, but the idea that you should be thinking about is that as if it's endless. And so, it's a very, very large, and you should be able to just make as many recursive calls as you need. But certainly, you will see that when you run programs on different processors, you will sometimes end up with some errors, and one of the reasons for that is because you ran out of memory. Okay, so just one other comment here is that the push and pop operations, which are all we need to use in order to have access to the stack, actually just consist of beta instructions that we already have available to us. So we're not actually adding any hardware in order to support this stack. It's really just software that we're adding. There are actually hardware implementations of stacks, but that's not the case in the beta. The other thing that, you should just be aware of is that there are also, different conventions that are used for different processors. So, in the case of a beta, we've decided that every time we're pushing to a higher address. In some other processor, you might find that they've made the opposite decision. So you just need to be aware of, with any processor that you use, what were the decisions that were made for that particular processor. Okay. So here we have 4 macros which enable us to deal with the stack. So the first 2 are push and pop, which we talked about a little bit already. And the second 2, what they allow you to do is basically allocate reserves a certain number of words on your stack, and deallocate takes those words off of the stack. And so this is great for when you need a certain amount of local memory. You can say, hey, skip this number of words in my stack and then continue adding after that. So we're going to look a little bit in more detail as to what exactly needs to happen for these operations. So what does a push want to do? Well, a push wants to put something into the location that's currently being pointed to by the stack pointer, and then it wants to increment the stack pointer to point to the next location, right? So we've got, here's our stack. We've got some, let's say that these are used portions, and my stack pointer is pointing over here, okay? When I do a push, let's say I just push a value x, what I'm expecting is that x will end up in this location, and that my stack pointer will now move down to here and point to this next empty location, okay? And so we can achieve that by, the stack pointer is just register R29. And so what we want to do is we're adding 4 to R29 because we're dealing with 4 bytes every time we have a word. And so in order to move the stack pointer down to here, we're simply incrementing it by 4. And then we're storing the contents of whatever it is that we wanted to push onto the stack into the location which is determined by whose address is the contents of the stack pointer minus 4. Right? So we just incremented our stack pointer to point to here. So I don't want my x to go here. I actually want my x to go here. And so I need to subtract 4 from that and store it there. Okay? My pop is very similar, right? We need to do the reverse. So if I have a value x here and I want to take it off the stack, I'm going to do a pop of x, okay? And what I'm expecting is that after I've done that, my stack looks like this again, and my stack pointer now points over here, okay? So what are the things that need to happen? I need to take whatever was at the location that was SP minus 4 off the stack and put it into my variable x, or my register x. And then I need to subtract 4 from my stack pointer to make it point to the now, first unused location. So does anybody see anything that they might consider a little strange about the difference between the push and pop? And specifically, take a look at when you're dealing with memory and when you're dealing with changing the value of the stack pointer. So what do we see as different here? Yeah.
In push, you increment the stack pointer at this person is pop.
Right. Do we have any idea why? Yeah.
That's the guard between. That's the guard from interrupting current between the two operations and possibly that could possibly miss the stack pointer.
That's exactly right. So later on in the course, we're going to be learning about interrupts, but you know enough about it today to understand that if I want to consider these push and pop instructions as essentially atomic, right? You want to do both pieces of them together. Well, it is possible, however, that after I executed one of them, but I still haven't done the other one, that my program gets interrupted. So what we want to avoid is leaving our stack in a situation where the stack pointer is not pointing to an empty location, okay? So by doing the instructions in this order, we're guaranteeing that, right? So instead of first putting x into here and then incrementing my stack pointer, that would be a problem if I got interrupted after I put the x over here, because my stack pointer would now be pointing to a location that's not unused, and if my interrupt code then used the stack, it would overwrite this value of x. So instead, we do it in the reverse order. I first make the stack pointer point over here. Now both of these locations are unused. Then, assuming I wasn't interrupted, I go and I store my x at the location pointed to by SP minus 4. Okay? And so this way, if I get interrupted between the two, I don't have a problem because my stack pointer is pointing to an empty location. Okay? The pop is exactly the reverse. Any questions about that? Okay. So allocate and deallocate are fairly similar. They're really just doing adds and subtracts to our stack pointer, which is a register R29. And again, because we're dealing with words, then every time I want to allocate one word, I'm actually incrementing my stack pointer by 4, or 4 times the number of words that I want to allocate. Okay, so let's think a little bit about what we said earlier, which is that what is the benefit? One of the benefits of stacks. One of the benefits of stacks is that it essentially can create additional storage for you once you run out of storage. So we said we have 32 registers. And let's suppose I'm writing some complicated piece of code, and I used all of my registers, but I want to have some more. So what could I do? Well, right here is an example of what I might be able to do. I can take, let's say I need 2 more registers. I can take what's currently stored in R0 and R1, I push it onto the stack. That means that the value that was in them is being saved. Now I have free reign to use R0 and R1 for whatever I want. Okay, so I execute a bunch of instructions that make use of R0 and R1, and now I'm done. So what was our discipline? What did our discipline say? Our discipline said you can use the stack whenever you want, just you have to put it back to the way it was before you started, right? So we're going to pop R1 and R0 off the stack. That will make sure that our stack is back to the way it was before we started this particular piece of code. And in addition, it's going to restore the values of R1 and R0. And note, of course, that we have to do this in reverse order from the push, okay? So if I'm pushing X or let's say R0 followed by R1, I need to first pop R1 and then pop R0 because of the way that the stack works, which is the last in is the first out. Okay, so let's take a look at how we're actually going to have these activation records work on our stack. So just to recap a little bit, we have what the caller needs to do is it needs to pass the arguments to the callee. We have to be able to have a place to store some local variables, and we need to be able to call other procedures, either a completely different procedure or make a recursive call to the procedure itself, like the factorial one. So let's first talk about what the caller has to do. So what the caller has to do is they're going to push the arguments onto the stack. They're going to do that in reverse order. We'll get to in just a couple slides why they should do it in reverse order. And then they're going to branch to the callee and save the return address in this special register called a linkage pointer. So register R28 is used just for storing these return addresses. And after you return, you want to clean up. So what does that translate into? If I have in C a call to a procedure which uses these expressions as the arguments to that procedure, then what I'm going to do is I'm going to evaluate those expressions in reverse. So I will first compile expression n, store that into some register, and now I can push that register onto the stack. And that means that I've pushed this last argument onto my stack. And then I continue with the next one, all the way down to the first argument, where I do compile expression 1, get something into Rx, and now I push Rx. So now I have on my stack all my arguments in reverse order. The next thing that I would do is I now call my procedure itself, and we learned how to do that already. We just use a branch instruction. So we branch to this procedure, and we store our return address, which is the address of the instruction immediately after this branch, in our linkage pointer register, which is register R28. Then when we return from the procedure call, it's our responsibility to clean up anything we put on the stack. So what did we put on the stack? We put the n arguments on the stack, and so we're going to call deallocate n in order to take all those n things off the stack. There's no need for us to do it one by one. We just want to clean up that stack, and so we can do it with one instruction. Okay. Now, the callee uses the stack for everything that it needs to keep track of. So let's see what that is. So the first thing that it's going to want to keep track of is this linkage pointer, which is the return address, right? So in order for it to be able to make recursive calls, you want to make sure that it keeps the value of what LP currently has in it. So the first thing that the callee is going to do is it's going to push the LP onto the stack. Okay? Now we have yet another special kind of register, which we call excuse me, why can't I think of the word? The base pointer, and this one uses register R27, and what this is going to do is it's going to basically give you a pointer into a particular activation record. And the reason that this is useful is because using that register, it's very easy to identify where exactly the arguments are for that activation record, as well as where the local variables are for that particular activation record. You could figure all of these things out based on the actual stack pointer register value, but it's a little more complicated. So it's kind of nice to have a variable that's just specific to one activation record. So the next thing that we're going to do is, in order to support recursion, we're also going to want to save this BP register. And so we're going to put that on our stack as well, okay? So callee so far has put the LP and the BP onto the stack. Our stack pointer points to the next empty location. And now we're going to set our base pointer to point to this same location, okay? At this point, we're ready to start putting local variables onto our stack. And so we would store, save as many locations as we need for local variables. And then if we needed to make use of any registers, we would make sure to save them by putting those onto the stack next. And so we would save those registers. So let's take a little bit of a closer look at what this really is going to mean in just a couple slides. But before that, let me just mention once again that the base pointer is just a convenience, right? We could do everything with a stack pointer, but using the base pointer, we'll see, makes things a lot easier. Okay, so let's get back to our previous question, which is, why did we put the arguments on in reverse order? Any ideas? Okay, so let me tell you. So the reason that we want to do this is because you might not know ahead of time how many arguments your procedure is actually going to have. Okay, there are procedures that have a variable number of arguments, and you might, need to look at the first argument in order to figure out how many other arguments you need to be looking for. And so if we put the arguments on in reverse order, then what's going to be true is that argument 0 is always going to be located 3 words before this base pointer. Okay, so it's very easy for us to find the location of that first argument, and once we've read that first argument, then that might give us all the other information that we need in order to determine how many other arguments we need to read. Okay, and so we put them on in reverse order, and we're going to, next what we're going to see is how do we go about accessing them. So here's what my callee's stack looks like. So you have your arguments in red here, which were pushed on in reverse order. You then have your saved LP, saved BP, your whatever local variables you put on, and then you store whatever temporary variables plus whatever registers you're going to use. Now, if I want to access the jth argument, we said that for argument 0, it's always located at BP minus 12, right? The contents of register BP minus 12. If I want to just get a random, argument j, that's always going to be located at register, the contents of register BP minus this equation 4 times j plus 3, okay? But the key is that we always know exactly where to find each argument relative to the base pointer. Similarly, to access our local variables, we know that the first local variable, local 0, is always located at the base pointer. And then if you wanted to access, the kth one, it would be at BP plus 4k. Okay, so at this point we're done, and we now have a contract which tells exactly what the callee needs to do, what the caller needs to do. So let's summarize that contract quickly. So the caller, what it's going to do is it's going to push the arguments onto the stack in the reverse order. Next thing it's responsible for is to pass the control to the procedure itself. So it's going to branch to that procedure, and it's going to store the return address in this register LP, which stands for linkage pointer. And when we return from that procedure call, it's going to remove any arguments from the stack in order to make the stack look like it did before it began. On the callee side, we're going to have it perform whatever computation it needs to perform for the execution of that procedure, and the expectation is that the result is going to be put into R0 so that the caller knows where to look for it. It then branches to the return address, and it needs to also make sure that it's leaving the stack intact. So anything it pushes onto the stack, it needs to take off. And finally, all the other registers, you have to also make sure that if you're going to be modifying them, you need to have first saved them so that you can then restore them before you return from your procedure call. Okay, so if we actually look at the 3 sort of different pieces that go into this, what we have is our calling sequence, where we would basically do a number of pushes of our arguments in reverse order, followed by a branch instruction that calls this procedure or function f and stores the return address in LP, and then you do a deallocate n once you return in order to take these n arguments off the stack. On the entry side, when this is the beginning of the procedure code, what we're going to do is we first push LP, then we push BP, then we move stack pointer to base pointer. This now makes the base pointer and stack pointer point to the same location, which is the one immediately after the stored BP value. And then you allocate space for your locals, and if you're going to make use of some registers, then you would save those registers. On exit, you basically want to undo that. So if you pushed some registers, you would want to pop them, and of course you want to pop them in reverse order, just like we saw in the example with R0 and R1. You would then get rid of all of your local variables by moving this base pointer into the stack pointer, and once again making those two registers point to the same thing. So notice that we don't actually need a deallocate instruction over here to match this allocate instruction, because this move already takes care of that for us. And finally, we pop our base pointer, pop our LP, and then jump back to the LP. And if we follow these conventions, then we can run recursive procedure calls and everything will work just fine on our beta. Okay, so just to conclude, if we go back to our factorial procedure, this is the translation of it into beta. So we've got here our entry sequence, which looks just like what we said. We push LP, push BP, make the SP and BP equal, and then we save R1 because we want to make use of it. Our exit sequence is the reverse of that. You pop R1, push BP to SP, and then pop BP, pop LP, jump LP. And then in the middle, we have this recursive call, which is going to push a new value, which is the argument for the recursive call to factorial. This is n minus 1. This gets calculated here. We push that, we branch fact to factorial, and store the new value into LP. And so now when we return from the recursive function, we'll know to return to this deallocate. And finally, when we return from it, you're going to do a deallocate 1 in order to take the argument off of the stack. And the rest of it is just the functionality of this, the multiply and doing your subtracts and things like that. So if you walk through it, you'll see that this will work also for recursive calls to factorial. All right, thank you very much. I'll see you guys next week.